Let's do this problem from your lab assignment, section 7.8. This is problem number 2. Find the values of p for which the integral converges and evaluate the integral for these values of p. Enter your answer as an inequality. Okay, so this is our integral. We're going from e to infinity. So this is an unbounded limit. So that is our integral. That's our type of improper integral. And we have a number 18 divided by x, and then we have ln x raised to the p power. So what we need to do to write this integral properly is to replace this infinity with some finite number b, and then we'll take the limit as b goes off to infinity. And so we have a regular integral, or an integral that we should be able to find. And we can do that by using a u substitution. If you look ahead and say the derivative of ln x, the derivative of ln x is 1 over x, and that is the x in the denominator that's going to cancel. So if we let u equal to ln x, du is going to be 1 over x dx, as per our u substitution. And so we're going to replace this with dx over x. We're going to replace that with just the du, and then we need to deal with the limits now. Since we're switching to u, let's change our limits to u as well. So u is equal to ln x. Then by putting the lower limit e in there, we're going to get ln of e. Ln of e happens to be equal to 1. And then we have ln of b, but if we let b go off to infinity, the ln function also goes off to infinity. So infinity. So the limit is also going to go off to infinity. So now our integral becomes an integral from 1 to infinity. Now there's an 18 in there somewhere. And then we have x dx is going to get replaced with du. And so all we have left is ln x raised to the p. But ln x in our u substitution was equal to u. So that's just going to give us a u to the p in a denominator. So now we learned that the integral of something over u to p converges to, well, this is an 18 over here. This is going to be u raised to the p, that's actually negative p, and then plus 1. And then we divide by negative p plus 1. And then we put 1 in infinity, or 1 in b, and then if you let b go off to infinity, this thing's going to go to 0 for some special values of p. And the special values of p is that if you imagine that this thing is going to be bigger than 1, then this is going to be a negative, which means it's going to be in the denominator. And if you let the denominator go off to infinity, this thing's going to go to 0. And so it's going to approach a particular value. However, if p is equal to 1, if it's equal to 1, this is just a constant, and this is going to diverge. And if p is less than 1, then this is going to be a positive number, and that positive number will make this diverge also. So I think our solution is just going to be, after you put the limits in for u, it's just going to be putting 1 in there for u. which is going to give us 1 divided by 1 minus p. So I don't think that worked out very well for us. Let's try that again. If we actually worked out the integral, this is how the integral should look like. We have the integral is actually equal to the limit of something where it's finite, and then the antiderivative of this is 18 u raised to the negative p plus 1 divided by negative p plus 1. We put in the values for t, and we get this, and we put in the value of 1, and we get this, where we're subtracting. Now, as t goes off to infinity, and for appropriate values of p, like p bigger than 1, this whole thing is going to go to 0, and so what we're going to have left is going to be this expression. And it turns out that this expression is not quite what I had earlier, which is why it was marked wrong, but it would be negative 18 divided by negative p plus 1. And so I think that was our errors because we didn't put that negative sign. I didn't put that negative sign. So let's submit. Okay, now it looks good. Of course, a nicer way of saying this is to distribute this negative sign, so you get negative 1 and then positive p, so we get p minus 1. So this is our convergence. Okay, I hope that helps.